Hello everyone, my name is Paul Albert. Welcome to my presentation, where I'm going to present to you the work that I'm doing on utilizing unsupervised domain adaptation and super resolution to predict dry herbage biomass expected harvest using drone images. I'm a third-year PhD student. I work at the Vista Milk Science Foundation Ireland Center here in the Dublin City University in Ireland. So the problem that I'm tackling in my research is given an RGB image of herbage in the field on the farm, predict different characteristics for this herbage. So the characteristic I'm interested in my research on the right of your screen. And so these herbage pictures are pictures of grass and clover mixtures that are being fed to cows. And so the main interesting research aspect of this problem was that I designed a model that solved this problem, but only on high resolution images that are taken close to the ground as to capture as many details as possible about the herbage. So images that were captured using tripod mounted cameras at a distance of around 1 meter from the herbage. And I'm trying to see in this research how I can adapt this existing model that works well and has low errors to a different type of data, which captures the same can of herbage, but from an aerial perspective. So in that case, using drones to take the pictures at an altitude between 8 to 12 meters. So to guide you a bit around my thought process when solving this problem, the first step was to just figure out that in the end, these drone images, they capture the same data just from higher up, right? So you just get a larger view of the field. So you should be able to crop a given area of your drone image, which would contain the same amount of elements that we had in these initial high resolution, highly detailed images that we have a working model for. And from there, we would be able to apply the existing model because we have the same amount of elements and they come from similar fields. But even if in our case, the drone was taken pictures quite close to the ground, between 8 to 12 meters again, and with a high resolution camera, so 5,000 pixels by 3,000 pixels in that case, because of the motion of the drone and because of compression artifacts on these very small elements in the image, and in that case, we had as well some color saturation, as you can see here. The images end up looking very different from the training data we have for the working model. So the existing model doesn't generalize well to these images that are quite degraded. You can see here a comparison between the images we have a working model for at the bottom and at the top, the images from the drone. And so my proposal here was to how can we enhance the quality of these drone images? And so this is done using a unpaired generative adversarial network, which is called CUT from the computer vision literature. And an important characteristic for this generative model was to be trained in an unpaired fashion because high resolution enhancing algorithm, super resolution algorithm, need to be trained using pairs of samples, right? So you would have as input your low resolution version of the image and as output the expected high resolution image, and you will need the network to enhance your initial image to look like your target image. But in my case, I only had the low resolution image, which are the drone images, and I don't have access to any higher resolution version of these drone images. So I really needed to have an unpaired training network. And you can see some examples here on the screen. So on the left, you have 3 different crops from the drone images that are being enhanced. You can see by the network here on the right to be of higher resolution, and as well the colors are corrected a bit and the motion blur is removed. And so now these images, which are taken from the drone images again, look very close to the existing data we have, that we have again a working model for. So it's much easier then to transfer a model learned on this data to this enhanced version of the drone images. So the second part of the algorithm involves some semi-supervised regression. I won't go into many details about it. There's some specific issues that need to be tackled for regression. But if you're interested in talking about it with me, please come to the poster session and engage me on it, or post questions online if you can't attend in person, and I'll be happy to discuss this further. To go quickly over the results, so the way the algorithm works is then, given a drawn image, you will crop out the image in a chessboard fashion into small squares. And these small squares are then enhanced, and a prediction is made on the enhanced version of these squares. And this gives you a resolution that's quite small, quite fine on the ground. So we're talking here 50 by 50 centimeters on the ground. And this allows applications to very specific defects in the field. So you can see here, for example, a small area in the field that doesn't contain any grass, and the algorithm detects that this area doesn't contain any grass and predicts expected harvest for this specific area of the field to be very low. So that's one part of the evaluation that I proposed in the paper. And the other part is to compare against human experts. So the farmers that do estimate these characteristics we're interested in, especially here, the expected harvest mass visually. And I found that the algorithm performs on par with human, so gives accuracy numbers very close to the humans expert. So that's very encouraging for future research. So a few words of conclusions, and mainly more about the impact this algorithm can have on farmers. We're thinking now of deploying this algorithm into farms, where farmers would input a set of GPS coordinates in the software, where they want the drone to go and take pictures on different parts of the farms. The drone would go then automatically to these areas, take pictures. The pictures would be analyzed either on the drone directly or on the cloud, in the cloud. And then we would return to the farmer an accurate map of what's happening on his farm, and maybe guide him towards areas where the expected growth is slower than what was expected. So maybe some fertilization is needed in this area of the farm, or some part of the farm requires more clover to be seeded because they didn't come up during the seeding season. And so that would help farmers manage their farm. So thank you for listening to my talk. And if you're interested in talking about this more, come see me at the poster session. I'll be happy to discuss with you. Thank you.